when we look at the example of the RSSI, and we're talking about an antenna, remember that distance is an important factor for us, right? The strength of that signal is going to get worse and worse as distance goes by or goes away. So when we look at some of the original access points that were giving us, or frequencies that were giving us 54 megabits per second, things identified by like 802.11a or G. You might not always get 54 megabits per second, because to do that, the minimum I need is minus 79 dBms, and that means I might have to be really close to the antenna to be able to get that kind of strength. If I'm further away, so far away, let's say that I'm way over here at minus 91 dBms, I might be lucky to get 9 to 6 megabits per second. So what's happening is that it's harder to receive because I'm not at a maximum level, and so your throughput actually goes down as you take your distance away. Now, if you add into that some sort of an interference, let's say my microwave oven here, well, when I first grew up with them, they were called radar ranges, and they had knobs instead of push buttons. So that's what I'm drawing. Or you could think of it as a TV, but it's a microwave. So it's providing some of that interference, right, that noise floor stuff. And that noise floor is also going to take away from the dBms that I receive. So I could be very close, close enough to get, let's say, 48 megabits per second. But because of that ground floor or that noise floor coming at me, I might actually be only able to get 36 megabits per second. I hope you understand then why this type of mathematics we've been doing helps us understand locations of where we place the antennas so that we can get the best signal out to the most people and have good quality communications.